Hello, everyone. This is Stephen Hardy, Editorial Director and Associate Publisher of Lightwave. And it's my pleasure to welcome you to today's Lightwave Online webcast, in which we'll discuss troubleshooting coherent optical communication systems. Our webinar today is sponsored by Keysight Technologies, and we thank them very much for their help in making today's event possible. So, of course, coherent transmission is now well established as the best means to support line-side optical transmission rates of 100 gigabits and beyond. And that means there's a widespread need to understand how to troubleshoot systems based on coherent transmission. That's why I am very happy today to moderate this webcast, which will feature a presentation on the topic from Michael Königsmann, who is an application specialist within the Digital and Photonic Test Division of Keysight Technologies. Michael joined Keysight in 1996 as an application engineer for RF and microwave products in the electronic test and measurement business. During his 19 years with Keysight, he's held a variety of positions: sales, product support, R&D, and product marketing. Currently, he's working in product marketing for Keysight's Digital and Photonics Test Division, as I mentioned, focusing on applications for the optical modulation analyzer and high-speed arbitrary waveform generator product portfolios within coherent optical communications. Now, before I turn things over to Michael, let me review a few details of our brand new webcast tool. First, if you're not happy with the size of your presentation screen, you can change it either by clicking on the maximize icon on the top right side of the window, or you can grab the bottom right-hand corner of the slide window and drag it with your mouse to the size that you prefer. Next, you also should see a row of function buttons and boxes at the bottom of your screen. One of the most useful of these will be the Q&A box, which should already be open next to the title slide. I'm hoping you'll feel free to ask questions at any time during our event today. To submit a question, you can click on that Q&A box. If it's not open, type in your question and hit the submission button, and your question will be added to the queue. We'll get to as many questions as we can after Michael finishes his presentation. As usual, we don't plan to reveal the names of anyone whose questions we choose to answer today, so you'll be able to participate anonymously if that's important to you or to your company. Now, in the past, if you've attended one of our webcasts, you may recall that if you've had a technical problem, we've asked you to alert us through the question box as well. But now, as you can see, we have a button devoted to helping with any problems you might run across. So in the unlikely event you're having audio or other problems, you can click on that help button, which will provide solutions to the more commonly encountered issues that you might have. If the info there doesn't help you, though, yes, indeed, go back to the Q&A box and let us know what's going wrong by submitting your problem that way, and our webcast technician will address your problem as quickly as possible. Now, one of the things that isn't new is the fact that this presentation will be available on demand from our webcast archive for the next several months. We'll send a reminder email message to you and everyone else who registered with a link to the archive, and the archive version of the webcast will also be accessible from the webcast archive section of our website, which you can reach via our homepage at www.lightwaveonline.com. If you're interested in getting a copy of the slides you're about to see, the folks at Keysight have informed me that they'll follow up with each of you after the webcast via email to tell you how to receive them. And with that, let me turn things over to Michael Königsmann, Application Specialist within the Digital and Photonic Test Division of Keysight. Michael?
Hello, everybody. This is Michael Königsmann, as Stephen already said. Thanks for the introduction, Stephen. Let's get started with the coherent optical communication system troubleshooting in today's webcast. We will have a short agenda. We will have a look at market and technology trends. We will bring some light on coherent measurement challenges, as well as a variety of typical tests that are done in coherent transmission systems. We will look briefly at some impairment emulation that we can do already in the electrical domain to test coherent systems. Also, I'm going to show a couple of tools to generate signals that are commonly used in coherent optical applications, as well as a brief overview on optical IQ modulator And last but not least, a couple of tools to do some analysis on coherent systems or signals. And in the end, we see a couple of references. So in terms of technology trends, there's currently a movement into where people tend to use more and more bandwidth in current applications, so mobile apps and services. We have high-resolution devices that are eating up a lot of bandwidth, and last but not least, we see a lot of things going on around the Internet of Things, where even your refrigerator is connected to the Internet. These applications mainly drive high-speed I/O networks and also the throughput in data centers. And there is an outlook that by 2020 we will have almost 20 billion devices connected to the Internet. So that gives us quite of a challenge to keep up the transmission in the backhaul, increase the bandwidth cost effectively, and also to be able to release new technologies in time. There is a couple of things we could do to increase the capacity on existing networks. One is increasing the symbol rate of your modulation, typically 32 gigabaud and even beyond. There's another trend to maximize the bits per symbol, so using higher order modulation schemes also helps to make use of the available bandwidth much more efficiently. Besides that, we see multi-level signaling in digital links for data centers or in between smaller subgroups. And also there is a trend to use a different number of carriers, so OFDM or discrete multitone is the keyword here. All these can be used to maximize the transmission within the physical layer. And often we see a combination of these technologies. So basically, one movement is from on-off keying as we used to have it in the past years to coherent detection, where we now have the information not only in the amplitude of the signal but also in the phase embedded. You could easily double the bandwidth by using different polarizations in a fiber, so that would give us essentially a second channel to transmit our data. Another, as I said, is increasing the order of the modulation formats from BPSK to QPSK and even to some very high order modulation schemes like 164 or even 1024 and higher. And the last movement we see is discrete multitone or OFDM. Another technique that could be used to get more data into the existing bandwidth is the use of time domain pulse shaping, where people cut down the bandwidth of the individual signals. Here we see a variety of 4 different spectral bandwidth usages. The first one shows the narrowest bandwidth. The next one shows the best EVM. The third one is the best eye-opening, and the lowest jitter on the bottom. So there's no rule of thumb that says this is the best modulation scheme, but you can guess from the spectrum on the right-hand side, the green trace, that it makes a difference in the spectral use of these kind of signals as well. In terms of requirements for the application in coherent optical communication, as I said, we need more and more bandwidth. 100 gigabit is deployed. People start talking about 400 gigabit and even a terabit per second. That gives us a couple of requirements for the test equipment or the test instruments that we are going to use for testing these kind of devices. So first, the flexibility is of very high interest, so to be able to have different modulation schemes available. Also, it's very important to have clean signal generation so that you're not testing your device, you're not testing your instrument with the signal you're generating. Also, bandwidth of at least 20 gigahertz is needed to be able to fulfill these terabit transmissions. And also, it's very important to have 4 precisely synchronized channels to support dual polarization on the transmit side. On the bottom, we see typical screens from our analysis tools, the optical modulation analyzer, starting from QPSK, which is a rather simple modulation scheme. QAM 128 is more complex and it's sometimes used, and the right-hand side shows a little the outlook on an orthogonal frequency division multiplex signal. As I said, there's also a movement to emulate optical distortions or impairments already in the electrical space. That means we are able to generate deterministic and precise distortions on the signal by generating the behavior of an optical link already in the electrical domain. So in a traditional setup, we would use a pattern generator to get the digital data. Then most of the time people use a golden receiver or a line card or a reference transmitter. Then they launch this signal into their network or test bed, and finally they run an OSNR generator, which is basically adding some unmodulated light or reducing the optical signal to noise ratio. And with that signal, you stimulate typically your device on the test, and in an error detector connected to the output of the device on the test, you start counting errors or you measure the behavior of that receiver under certain stress conditions. This is a rather complex setup and it's not really repeatable over time. So one approach could be to use our new M8195 arbitrary waveform generator, which is prepared to generate these kind of behavior of the network or testbed already in the electrical domain. And then it could be a conceivable setup to use the AWG to stimulate your device on the test electrically, and then you start error counting and on the output. Or you extend the arbitrary waveform generator with an E to O converter or an optical modulator, and then you're able to generate a optical signal that already looks like it has traveled through a long network transmission. And in the end, again, you have your error detector available. Another third setup or scenario could be using the arbitrary waveform generator with its 4 outputs and stimulate directly the receiver section of a device or of an optical receiver. Just stimulate the electrical inputs, and you can do measurements and evaluate how these DSP algorithms work on specific stress conditions. In coherent applications, we see the AWGs, or arbitrary waveform generator, as really a good device, as it can modulate almost endless modulation schemes for even higher data throughput. It can generate signals, clean signals up to 32 gigabaud and even beyond that. And also it provides 4 independent analog outputs for dual polarization optical applications. Another new thing that we offer with the arbitrary waveform generator is what we call the out-of-box calibration, which allows us to already use a calibrated output on the front panel of the instrument to achieve a clean signal at the output directly, or even with some advanced techniques, extend that calibration plane to the input of your receiver. Another new development is the emulation of optical distortions already in the electrical space. What that means is shown on the lower left-hand side on this screen here. We are showing a dual polarization QPSK signal that has been artificially degraded in terms of phase noise. So I'm adding some phase noise on the signal, and you see how the constellation points start to rotate and don't look like a circle as we expect it to be in a perfect or more or less perfect condition. Also on the right-hand side, lower right-hand side, we show the user interface to generate these kind of impairments For those of you who are interested here, it's a 2 megahertz laser line width that I'm simulating right on the left-hand side here with my arbitrary waveform generator. So the Keysight M81, oh that's a typo, M8195A provides leading performance up to 65 gigasamples of sample rate, more than 20 gigahertz of bandwidth. That's good for signals beyond 32 gigabaud in symbol rate. It offers out-of-box calibration, and it's available in 3 different versions, 1, 2, and 4 channels. Basically, it's possible to go in testing where you have not been able to test before in speed, bandwidth, and channel density. The picture on the right-hand side shows a NRZ signal on a 32 gigabaud per second, and you see how nicely the eye is opening on this signal here. So what are the challenges we are facing in coherent applications? Typically, we need clean signals in electrical and optical domain. We need the clean signals at defined positions or test points in the setup. High data rates are required. Also, it's mandatory or very helpful to have accurate and also very important repeatable test signals available. Distortion emulation becomes more and more important, as well as the ability to generate flexible modulation from it. What that means, as I said, we have out-of-box calibration available in our arbitrary waveform generators. That means I have a reference plane at the front panel connectors. If that's not enough, I can do something that we call the in-situ calibration, which basically extends the clean signal towards the input of your device on the test. This in-situ calibration can be done with S parameters of your channel, and these S parameters could describe the frequency or phase behavior of your channel, and they can be embedded or de-embedded. And also it's possible to do live frequency and phase response measurement in system using our vector signal analyzer software or the optical modulation analyzer software. What that does, I'm showing in one of the next slides. To give you an idea what happens, I have 2 screens down here. One is showing the QPSK signal at 32 gigabaud without correction, and you see the constellation points are kind of smeared out. With correction, the constellation points show up very nicely grouped together where we would expect them. Also, on serial data, I have a 6 gigabit signal, a little bit slower than the 32 gigabit, but you can see the difference here as well. Without correction, the rails are kind of noisy and the transitions are a little bit noisier. And with correction, I get a really clean signal on the output of my arbitrary waveform generator. I'm going to show now how we are supposed to do this out-of-box calibration and especially the in-situ calibration. Typically, you would use either our optical modulation software or our IQ tools. IQ tools is a collection of programming examples that are available from our website based on MATLAB. You can use them to generate a very high amount of different modulation schemes. Both softwares talk to the arbitrary waveform generator, and they can be used to download signals into the arbitrary waveform generator. And also, we would use an Infinium series oscilloscope from Keysight as well, which is part of our optical modulation analyzer. And the calibration works like this. We download a signal into the arbitrary waveform generator. Then we hook up our amplifiers that we are probably going to use to stimulate our modulator. So in this case, I'm trying to get the frequency response out of the signal path and also the cable distortion or cable losses out of the signal path by connecting the output directly to the oscilloscope. And I'm using our vector signal analyzer software or the optical modulation analyzer software, which basically runs on top of the VSA software to look at the constellation, the spectrum, and also look at the phase and frequency response of the signal. I could also extend my setup to do the second polarization or the second pair of signals, IQ pairs at the same time, getting me to the 2 constellation here. And now I'm using a function of the VSA software that allows us to run an adaptive equalizer on the signal that is able to measure the phase and frequency response of the signal. And I'm taking out this phase and frequency response data and load it into my optical modulation software or the IQ tools. And the routines inside the software packages now pre-distort the signal in a way that the frequency loss and phase changes on the signal and also on the amplifier will cancel out with the pre-distorted signal. And in the end, I get a clean signal at the output of my amplifiers or at the front panel of the oscilloscope here. This could be extended to also some optical components. We did experiments already on a dual polarization Massender modulator where we use exactly the same setup, use the optical modulation generator tool, download the waveforms into the arbitrary waveform generator. We run the signal through a set of amplifiers to boost up the signal level, use a tunable laser source as a source for the modulator itself. And then we run the signal through optional amplifiers and fibers if needed. And in the end, we feed the signal into our optical modulation analyzers, the N4391A or the 92A. And then these analyzers are able to get the phase and frequency response out of the signal. And we can, again, take the phase and frequency data and download it into the optical modulation generator to pre-distort the signal so that we get in the second run a clean signal at the end of our devices here. So that would be the end-to-end calibration of the whole transmission system. And you need to be aware that this already includes the characteristics of your receivers. That's an important thing to know. But these instruments get calibrated in the factory, so the response or the results are known results, and there shouldn't be any surprises. Typical tests that we are seeing in coherent transmissions is the next sections I'm going to talk about. So a typical application we see is what we call the system and link stress test, where you have your transmitter, you run it through a set of amplifiers and pieces of fiber in between, and then in the end you hook up your receiver module. Typical test that could be done here is the bit error rate, or the EVM versus power or versus optical signal to noise ratio, by tapping the signal after amplifier stages or anywhere in the transmission. Another measurement that could be done here is the spectral behavior, looking at neighbor channels, see how the distortions are amongst the two. Signal integrity could be checked, as well as nonlinear characteristics like PMD or PDL, and even CD, chromatic dispersion. Distortion is possible to measure with the optical modulation analyzers. Another application or another scenario could be a receiver stress test with our arbitrary waveform generator and an optical modulation generator. I'm showing here the optical multi-formant transmitter from ID Photonics, or the Heinrich Hertz Institute here in Germany, which we tested extensively together with our arbitrary waveform generator. And I'm using a tunable laser source on top of that setup here to get my laser signal. I modulate that signal and feed it into my receiver module. And now I'm able to do measurements on the receiver. I can vary the losses on the signal. I can change the polarization. I can add polarization, more dispersion, distortion. I can lower the optical signal to noise ratio, and I can also add nonlinearities to the transmitter and see how my receiver is behaving with that kind of stress applied. That was the optical transmission. It's also possible to think about using just the electrical part and stimulate the receiver electronics of the receiver processing part of your receiver with the arbitrary waveform generator directly. And again, it's possible to generate a number of modulation formats for research and development applications. It's possible to have high quality pulse amplitude modulation signals, pump 4, pump 5, pump 8, whatever. Dual polarization, QPSK, and even higher order QAM modulation is possible. It's even possible to generate non-standard arbitrary constellations for advanced research. Again, bit error rate testing is possible as we are able to generate known PRVS sequences on the arbitrary waveform generator already. We can even provide return to zero signals, dual QPSK, support of 56 gigabaud, and beyond that it's possible to be able to run 100 gigabit research and even higher. And we can test basically the receiver algorithms for robustness on distorted signals. Another application could be testing of IQ modulator behavior, where we stimulate the input of an IQ modulator with the arbitrary waveform generator. Furthermore, if it's possible to access the local oscillator input of the IQ modulator, we can replace that with a tunable laser source as well, and then run our tests here, hooking up one of our optical modulation analyzers to do some analysis on modulation quality and the polarization behavior. And if that's not enough, we can even use our light wave component analyzer family to get the S parameters and the phase and frequency response of the individual path inside the modulator. Typical tests with the optical or with the arbitrary waveform generator here is the cutoff frequency for each of the paths, in application tests to specify best EVM performance, and also polarization behavior as well as phase response and skew are possible. And another section could be tested here, that's the modulator bias control. You get easily an indication of the behavior of your modulator bias control. So in coherent testing, we see typical measurements here. I picked like 11 different measurement results that we can measure with our optical modulation analyzer software. And this is not a complete list, but I picked out like 11 of these as I found them the most asked questions regarding these kind of measurements. And I'm going to show some more details on the typical measurements we are doing. The first one we look at, if we are doing these transmitter testing, is the error vector magnitude, or for those of you who are used to digital transmission or to just on-off keying, it's the Q factor, basically the eye opening. The error vector, for those of you who are not familiar with it, is basically a measurement where I compare a reference constellation point or a reference vector with a measured constellation point that I can also describe by using another vector. And then the difference between these two vectors is considered to be the error vector. And for our measurements here, we are concentrating on the magnitude of that error vector, and we call it the error vector magnitude. It is more or less a figure of merit and gives you a first indication if you have a rather good or more or less a bad signal on your transmitter. We see in the screenshot I have here, we see the EVM reported as well as the Q factor reported on the screen. And also, here's a little explanation how the Q factor is described. It's basically the signal to noise at the decision points calculated, and there is a relationship. The Q factor is more or less equivalent to 1 over the EVM that I'm measuring. And to give you an idea what the numbers are on typical EVM values for 2 or 5% EVM, for instance, we get like a Q factor of 20. The 10% EVM correlates to roughly a Q factor of 10. So that was the first measurement we do on the optical modulation analyzer. Then we have a rather new measurement on the optical modulation analyzer. That's the EVM percentile. The EVM percentile basically defines a radius of a circle around a grouped measured constellation point centered at a reference constellation point. That means I have my constellation points measured on the left-hand side here in that screenshot, the blue constellation that I'm showing. Behind that, I have a reference constellation. That's not visible here. We see it in one of the next slides. And I'm comparing each measurement I'm doing with my constellation reference. I have a zoomed picture below here on that page, rather in the middle, that gives you an idea what I'm talking of, hopefully. We have the reference constellation in the middle as a green point, and the red dots should indicate the measured points that I'm measuring. And now I draw a circle with a specific radius which correlates to the EVM percentile. And the new thing about this measurement is, in contrast to the classical EVM, the EVM percentile does not include IQ imbalance and quadrature error. And also, it's not an RMS average value, so it gives you a better indication over longer-term measurement what's going on your transmission. There's also a hit ratio mentioned in the context of the EVM percentile, and the hit ratio multiplied by the number of points you measured gives you the number of points that are outside the circle that we see here. And for Gaussian-dominated distortions or impairments, the classical EVM and the EVM percentile kind of converge if we enter a hit ratio of roughly 0.3, 0.2. And this value can be set in the EVM percentile algorithm of the optical modulation analyzer. And on the screenshot here, we show both the classical EVM, the EVM percentile, and also the number of symbols we already counted to do the math. Another measure that we look at, especially if we try to find the operating points for a modulator, is the gain imbalance. It basically compares the horizontal, the I, and the vertical Q amplitudes. And we come to the conclusion here on this picture that obviously the horizontal amplitude is slightly higher than the vertical one on the constellation. You may see the yellow constellation, which is the reference I'm comparing against. And this gain imbalance could be caused by different amplitudes in the driving inputs, for the driving inputs of your I and Q modulator, or it could be a wrong setting in the IQ bias or in the modulator bias. Also, this imbalance could be seen in the eye diagram of a signal that we see on the right-hand side here as yellow and green eyes. You see that the green eye or the green signal is slightly higher than the yellow signal, corresponding to the signals in the constellation diagram. Another measurement we do, or we can analyze, is the IQ skew. If you look at the constellation point, you see that the 45-degree transition kind of open up, and they're not a straight line between the constellation points anymore. That's the first indication that something's wrong with the timing of your I and Q data signals running into the modulator. Also, if we look at the eye diagram, we can clearly see the timing difference between the green and the yellow trace. And to make life easier for you, in the optical signal properties window of the optical modulation analyzer software, we show the skew between I and Q reported in picoseconds or femtoseconds. And also an indication for bad skew settings could be an increased EDM value. Another measurement that's often done is what we call the IQ offset. The IQ offset is an offset in the DC component of your driving signals. Again, we see the two eye diagrams here, but unlike the pictures we saw before, now we have just different DC levels in the two eye diagrams. So the green one seems to be slightly lower than the yellow one. That means my constellation is not centered in the middle of the constellation plane here. Again, we show the yellow reference, and you see the blue constellation is slightly shifted towards the 6 or 7 o'clock position on the screen. And again, the optical modulation analyzer software shows the IQ imbalances and IQ offsets also for the complete signal and as well as for the individual contributors for I and Q. And if we would have 0 DC offsets, the IQ offset will become 0. So that means I'm seeing a minus infinite dB value reported. Another quick check that you could do on the instrument is looking at the spectrum. So in case you have DC offset in the signal, you would see a little carrier spike here in the middle of your spectrum. The red one shows actually the carrier feed-through, and the yellow one does not do it. So in the red case, in case of the red trace, I'm looking at a distorted signals where I have some DC components running in the modulator. The next measurement is the quadrature error. That typically shows up as a distorted constellation, as we can see here on this picture. Again, we see the squared reference in contrast to the slightly distorted constellation points here. It indicates the orthogonal error between the I and Q quadrature phase. So typically this angle should be 90 degrees, but in this screenshot here we see that it is obviously not 90 degrees anymore, and the measurement result window shows you exactly what the actual value is, and it reports an error of 23 degrees. So that means my constellation is only 67 degrees in angle between I and Q. The results could come, or this result could come from IQ modulator bias settings in the 90-degree phase shifter. So if you consider a single polarization modulator, you have your I and Q modulator, and then the phase shifter in one of the paths, and if that phase shifter is not set correctly, you would see this kind of distortion in the eye diagram. Also, we report the frequency error on the signals. So if there is a mismatch between the carrier frequency and the receiver carrier, or the receiver frequency, center frequency, you would see that error reported in the signal summary here again. In this picture, we see a 2 gigahertz frequency offset on the signal, and it's hard to see because we are showing a almost 30 and above gigahertz spectrum. It's hard to see the 2 gigahertz change here, but you could guess that the yellow trace is slightly shifted to the right, indicating that there is a 2 gigahertz shift in the signal. This frequency error is, there is a maximum allowable frequency error, and this depends on the modulation scheme. And I have pointed out a list here for the different modulation formats and the maximum allowable frequency offset. So it turns out that the more simple modulation schemes are more tolerant. The QPSK, for instance, is almost 10% of the symbol rate that we can track. A QAM 256, we are already down to like 0.3% of the symbol rate. So the higher the modulation order goes, the more precise I have to be in terms of the matching between transmit and receive frequency. Another frequency domain error that we can analyze is what we call the symbol rate error. The symbol rate error shows up, if it's at a certain point, shows up as spread at constellation points in the constellation diagram. You see the red spots all over the constellation here. That indicates that I'm not exactly matched in terms of the symbol rate on the transmitter versus the symbol rate that I set on my receiver. And if I plot the error vector over time, which I'm showing on the right-hand side here, you see a typical V shape in the diagram here. That's an indication that something's wrong with the settings of your symbol rate. And also, I'm showing here, I was supposed to measure a symbol rate of 31.86 gigahertz, but the optical modulation analyzer tells me better, and it says it's only 31.7 something gigahertz. Obviously, there's a mismatch in between the two symbol rates here, and that leads to that typical V shape. So if you see this on the EVM versus time, you should check your symbol rates on the transmitter and the receiver. We can even provide analysis on dual polarization signals. Again, IQ skews are possible. We extend this here to skews between the two polarizations, the X and Y polarization. And we can also report errors in the amplitude of the signals in the two polarizations. Again, we have the optical signal summary that reports the most important parameters of your signal, starting with EVM, the symbol rate that's measured, the frequency error between the transmitter and the receiver, the skews between the two channels, the skews between I and Q inside the channels, IQ imbalance, and also the Q factor. The next screen deals with bit error rate measurements. It's possible to run very simple bit error rate measurements on the optical modulation analyzer software. It reports the actual error rate, the cumulated error rate, and also the bit error rate calculated from the EVM. So in this case, we see a very low BER calculated from the EVM, as my constellation points are really very dense, not spread out. But obviously, the bit error rate reports a much higher number here, 10 to the minus 3. So obviously, there's a mismatch in the data that I'm trying to analyze on the screen here. And again, we show the counted errors. We show the total errors that we've seen so far. Also, we can report the polarization delay between the two polarizations or the two signals. And also, we show what the PRBS generation details are. In this case, we have an IQ multiplex. Another thing to check for is delay in the PRBS generation. It's very common that only one PRBS generator is used, and it's split up, delayed, and it's used, the delayed part is used to drive the second polarization. If you are using a delay that is not sufficient enough to decorrelate the two signals, you may see strange effects in the constellation. Here I'm showing 6 different scenarios. Left-hand side on each of the 6 displays is the constellation, and the right-hand side shows the spectrum. So the first one is the 0-bit delay. So basically, it's I and Q running off the same data, and this gives you just a straight line between 2 of the constellations, in this case, the 45 degree. The spectrum doesn't look very strange in this case. For a 1-bit delay between the 2 data streams, we see a missing constellation already between the constellation in the constellation diagram here, and also you see a strange spectrum. There's a dip in the spectrum at some frequency. That gets even worse if I delay by 2 bits or 3 bits. You start losing another constellation or another transition between constellation points, and also you see a higher number of dips in the spectrum. So if you see something like this, it's probably a good idea to check the data generators and if there is enough decorrelation between the two I and Q data sources. By the way, this measurements were done on a PRBS with 2 to the power 15 minus 1. So that was the result, the analysis of optical signals. And as I said, we can also do some impairment generation already in the electrical domain. What that looks like, I have a couple of slides here that show what the user interface is on our optical modulation generator tool that talks to the arbitrary waveform generator. So here I'm showing the phase noise on the generator side. You have abilities to change the laser line width, for instance. You can change the flicker noise, the random walk noise can be changed. You can add a constant phase rotation to your signal if you want. And the lower part of the screen here shows you what the spectrum would look like in the simulation and what the model that we are using in the background looks like. And also the lower screen, the blue-red trace here shows you the time behavior of your frequency, of your phase fluctuation. How does that look in the optical modulation analyzer software? We are able to analyze the carrier phase noise as well. And we see here that the constellation points start to get more the shape of an arc. So I'm showing 3 different laser line width simulations here, starting with 500 kilohertz, 2 megahertz, and the last one is a 5 megahertz line width simulation. And you see how the constellation is more looking like an arc. As a reference, I plot a non-phase noise signal on the lower constellation screen here to give you an idea how that signal could have looked without the phase noise addition. And also the optical modulation analyzer provides means to measure the Lorentzian laser line width, the flicker noise, and also the random walk noise. That's the yellow box I'm showing on the lower right-hand side here. Another emulation that could be done with the optical modulation generator tool is the polarization changes on the signals. So in case we're using a dual polarization 4-channel arbitrary waveform generator, it's possible to simulate the behavior of a pole controller that is between the transmitter and the receiver. And this could be used to check the behavior of your polarization alignment in the receiver. I'm showing here a predefined pattern that's called the great circle, where we rotate the phase around the Stokes sphere on this screenshot here in the lower right. Another pattern could be selected that's called the slicer. It's more like a spiral that runs on the surface of the polarization, the Stokes sphere here in my generator tool. And on the receiver side, on the optical modulation analyzer software, I'm able to analyze these polarization changes as well. On the left-hand side, you see the great circle, and the right-hand side, you see the yellow trace of the slicer pattern that we run on the generator side. You may wonder why the constellation look a little bit odd. That's due to the fact that I have to rotate the phase very fast, probably faster than you would see it in a real-life application, to get the measurements done in this specific setup here. Another impairment that we can generate is the polarization or distortion. First order and second order is possible. Again, we see the user interface on the generator side, and I selected a 35 picosecond PMD and a second order PMD of roughly 900 picoseconds. And the result is on the next screen. The optical signal summary reports that we have algorithms inside the software that can compensate the PMD and also report the amount of correction that needed to be applied. And the result is shown here. The PMD is 34.7, and the second order PMD is roughly 1,000 picoseconds here. Not exactly the value that I said, but it's a very complex measurement here, especially the second order PMD. So a little distortion is seen here. So what are the tools that I use to generate signals for coherent optical applications? We have our arbitrary waveform generator, the M8195, sample rate up to 65 gigasamples per channel, 20 gigahertz analog bandwidth, 1, 2, and 4 channels. Differential channels are possible inside a single AXIE module. You see here on the screen a two-slot mainframe that has an empty space below the arbitrary waveform generator module. You could stick in an embedded controller here to get a very compact 4-channel arbitrary waveform generator, but it's also possible to look for 5-slot mainframes that allow even higher port count in one single module. In terms of memory, we provide up to 16 gigasample waveform memory per module. The amplitude can be set between 1 volt peak-to-peak to 2 volt peak-to-peak differential. The voltage window, so the DC offset, can be anywhere between -1 and +3.3 volt. We have very low intrinsic jitter, reported to be less than 200 femtoseconds for random jitter at 32 gigabits per second. We also have a 16-tap FIR filter in hardware for frequency response compensation. That allows us to change the frequency response and the correction on the fly without the need of recalculating the signal that I downloaded into the memory. You see a little asterisk on some of these bullets here. That's indicating that we are going to release a new version of that arbitrary waveform generator in October this year, and that will have the full functionality. Currently, we have a limited version available for those of you who are in need of doing measurements right now. How about optical IQ modulator to get optical signals? We have evaluated a couple of different optical modulators, and we found the optical multi-format transmitter by ID Photonics, or the Heinrich Hertz Institute in Germany. And we did extensive tests and did performance verification in the combination of the OMFT and the arbitrary waveform generator. And we are able to provide S parameters for the compensation of the modulator behavior, as well as RF cable compensation is possible. The modulator itself is good for up to 46 gigabaud for binary and 34 gigabaud for multi-level signals such as 16 QAM. We have dual polarization IQ modulators inside. Amplifiers are used up to 40 gigahertz inside. There's manual and automatic bias control inside module available. And also in combination with our arbitrary waveform generator, it's possible to apply pre-compensation to compensate the nonlinearities of the modulator, and also respect amplifiers inside the signal path so that we set the gain and also the wanted VPi on the optical modulation generator tool already, and it calculates the signal in a way that we get exactly to the VPi or the amplifier gain settings. So here I'm showing a small screenshot out of the optical modulation generator tool that I'm going to show here in more detail. So it's a dedicated software for optical applications. It generates 2 times IQ signals simultaneously. We can do optical impairments in the electrical domain already. We have signal path de-embedding available in terms of using S parameters or the VSA equalizer that I showed earlier in the in-system calibration. Here we see the pulse shaping window. We have different pulse shape filters available to do the pulse shaping. We can set the amplitude in another window. It's possible to select the electrical channel 1 to 4 and assign them to an optical horizontal I, horizontal Q, as well as we are able to compensate cable and skews in this screen here. So this picture allows us to add S parameter files for each individual signal path. Again, highlight on the optical modulation generator tool in terms of electrical simulation of optical properties. Phase noise is possible. First order polarization is possible to emulate with the tool, as well as first order and second order PMD. For the analysis side, we have a couple of tools available. It's our family of optical modulation analyzers, the N4391A, which is the optical modulation analyzer more targeted at R&D, 4 times 33 gigahertz, 63 gigahertz as dual instrument special available. We have 80 gigasample A to Ds running inside this oscilloscope that we use, and 160 gigasample for the 63. We can boost up the memory up to 2 gigasamples per channel, and we have the lowest EVM noise floor reported to be typically 1.5% EVM RMS, which is the lowest EVM that you could measure. The lower instrument here, that's our portable version of the optical modulation analyzer, compact, fully integrated, 4 times 23 gigahertz, slightly lower, but also it has 4 electrical inputs for dual polarization integrated receiver, coherent receiver testing. We also have a piece of software that does the analysis. Inside we use 63 gigasample A to D converters, and the noise floor is slightly higher, typically at 2% EVM RMS. So this is typically typical values. We see numbers even below the 2%. The software itself is pretty easy to operate. We have a smart setup inside the OMA software that allows us to set up the instrument by just entering 4 essential parameters. It's the carrier wavelength or frequency, it's the symbol rate that I'm expecting on the signal, and the modulation format I'm going to use or look at. And finally, you select if you're doing a back-to-back measurements or a link measurement. And if you're done, you press the OK button, and the instrument will do all the needed settings to get to a reasonable display. We have tabular results screens per polarization where we show typical optical properties. We've seen that already. We can do bit error rate in the individual polarizations, but we also have results that show cross-channel measurement results here. Again, the optical signal summary and the bit error rate. It's even possible to look at the individual tributaries in the bit error rate. And again, we have the widest selection of modulation formats inside the optical modulation analyzer software, from custom APSK to even OFDM. We can choose between 39 predefined modulation schemes. We can do amplitude phase shift keying. Up to 8 amplitude levels are possible. It's 256 constellation points, and even OFDM is possible. And here we see 2 examples. One, the upper one showing the APSK with that star-shaped constellation, and the lower one shows a typical OFDM signal. So in summary, Keysight's offering tools for coherent signal generation in form of the optical modulation generator and the arbitrary waveform generator. This can generate accurate and repeatable impairments. We also have tools to do analysis on signals, on coherent signals, in form of the optical modulation analyzer. And we have the arbitrary waveform generator available that provides 4 channels synchronized with up to 20 gigahertz and even beyond. So for further references, I have a list of literature in the end here, and that's pretty much the end of my presentation, and I guess we can open up the lines now for questions or comments from your side.
Very good. Thank you very much, Michael. Let's see. Before we have Michael answer the questions you've asked so far, let's let him catch his breath for a moment or two. And we have a few questions we'd like to ask you folks in the audience, 3 to be exact, which should take less than a minute combined. Our first one here is asking you to rate your overall satisfaction with this webcast. On this question and the others, if you could just select the answer that's most appropriate for you and hit the submit button, we'd appreciate it. We'll give you about 15 seconds to do that. In the meantime, you can start formulating some questions for Michael if you haven't asked them already. All right, time's up for that one. Our second question is simply yes or no regarding your interest in potentially purchasing the AWG for described today. Again, we'll give you about 15 seconds to answer that. And then after this, we have just one more question for you before we get to Key. And that final question is this one, which is, if you do have such an interest, how soon would you be looking to fulfill it? And we'll give you about 15 seconds to ponder your future. Share it with us. Great. And with that, it is indeed now time for Q&A. As I mentioned at the start of the program today, you can ask a question simply by clicking open the Q&A box, typing in your question, and hitting the submission button, which I see several of you have done already. I think we will have time to sneak in at least a couple of questions. Let's see. First, let's start with what is hopefully going to be an easy question for you, Michael. And that is a 4-channel AWG needed to perform all of the measurements that you described here today.
Well, if 2 polarizations are to be measured, it is helpful to have the 4-channel version available of the arbitrary waveform generator. So that makes life a lot easier if everything is in one box, so you don't have to care about synchronization between the channels and stuff like that. So the M8195 brings that by nature to synchronization.
Good. The next question I have is the presentation described the M8195A as having a sampling rate of 65 gigasamples per second. Is that a fixed sampling rate, or does the unit support a variety of sampling rates?
Well, 65 is the maximum, and we can vary that sample rate between 55 and 65 gigasamples per second. You may wonder how we can generate signals that are outside, and we can do fractional resampling on our signal that allows us to even provide signals that are not dividable or provide an odd oversampling ratio with regard to the sample rate.
All right. And finally, does the AWG only output electrical signals, or does it do optical signals as well?
Well, the AWG itself outputs only electrical signals. On one of the slides, I'm showing the optical modulation transmitter as well, the optical multiform transmitter. This is basically the extension of the arbitrary waveform generator into the optical domain. So to make it short, the AWG only puts out electrical signals.
Very good. And with that, unfortunately, we've come to the end of our program today. If we didn't get a chance to answer your question just now, or you're viewing this webcast from the archives, you can contact Michael directly via the email address that you should see here on your screen. I understand Michael also will be reaching out to as many people as he can whose questions we didn't get to as well. Before you go, Keysight has made available a free white paper that you can download right now as a thank you for your attendance today. Just click on the green folder that you should see at the end of the row of function buttons at the bottom of your screen, and it's all yours. As a reminder, several of you asked whether you can get a copy of the slides. The folks at Keysight will be contacting you directly via email with information on how you can acquire the slides if you'd like. Also, as I mentioned at the start of the event, this session will be archived within the next 24 hours. A reminder email message will be sent to everyone who registered with a link directly to the archive. And the archived version of the webcast will also be accessible from our homepage at www.lightwaveonline.com. And finally, I'd like to thank Keysight for their help in making today's event possible, Michael Koenigsmann for sharing his expertise, and of course, you in particular in our audience for attending. We have one more favor to ask you, which is to participate in a very quick survey that's about to pop up on your screens. Again, thank you very much for your attendance and attention. I hope you join us for our next Lightwave webcast, which will take place next month. Until then, have a great day, and goodbye.